Okay, then I'll start. Hello, everyone. Thank you so much for coming. I think I'm supposed to go through these instruction slides before I go onto the real talk, although being day 3, maybe you've seen those before. But here are instructions for turning on the captions, and also if you're having trouble, how to reduce the quality of the audio, of the video, or how to toggle noise cancellation. So the link to the slides is on the schedule in case you want to look at this or some of the links I'm going to be posting in here. And now, here we go. As I said, hello, my name is Emmanuel. I work at Google in the Munich office. And today I'm going to be telling you about NativeIO. NativeIO is our new storage API that has a particular focus on performance and genericity. Oops. Right, but first thing first, before I tell you about NativeIO, let me tell you what is it that we're trying to solve. The challenge that we're trying to tackle is to give developers storage that brings some of the good things from the native platforms, but preserves all of the good stuff from the web that we know and love. So that is to say, we want to give developers a storage primitive that is both very performant and very flexible, but of course is also secure, private, interoperable, and all those other attributes that we're used to by now. Some of the use cases where we see NativeIO helping out are, for example, bringing true and tried technologies like SQLite, LevelDB, or your favorite database to the web. And this is possible because of NativeIO low-level surface can support these higher-level storage concepts on top of it. So NativeIO would work as a backend for them. We also see NativeIO as enabling a fast and persistent fast and persistent file system for WebAssembly. And this is possible because when we're talking WebAssembly, we're usually talking either ported native code or maybe legacy code that comes with certain expectations on how data should be accessed, and also, of course, how fast this data should be accessed. And NativeIO is able to fulfill these expectations from that side of the applications. But we not only see NativeIO in this realm of like WebAssembly and ported applications, we also see it as a way to empower developers to really fine-tune the way that their applications access their data. So for developers that really want to squeeze as much performance as they can out of their applications, they can use NativeIO low-level building blocks and really construct the right storage algorithm that matches their needs. So yeah, these are some of the examples where we see where we could help. And without further ado, this is our interface. So as you can see, NativeIO is divided in 2 domains. Here on the left-hand side, you have the file system operations. And this is a very thin management layer to control the lifecycle of files. So with this set of operations, you can open a file, you can delete a file, you can rename it, and you can also list all the files that belong to an origin. If you look here on the right-hand side, it's the file operations, and that's really where the magic happens. So the first 2 operations, read and write, are arguably the most important, and they take a buffer and an offset. We take a buffer to minimize the amount of data copies we have to do, and the offset just lets us move this buffer within a file that already exists. With these kind of operations, you can also manipulate the length of a file. You can also ask the file handle to please move its contents from the memory to the disk. And of course, you can close a file handle to prevent resource leakage. In the next couple of slides, I'm going to show you a few examples of how this interface is used. As a fair warning, because NativeIO intends to be this very low overhead, low level API, the examples don't show anything too crazy. They do mostly what you'd expect. But I'll try to highlight some of either the quirks or the weird decisions we've made so far in order to squeeze the most performance we can. Here, the first example I have for you is on file system operations, in particular get-o and rename. I'll walk you quickly through the example here on the right-hand side and then highlight some of its parts. So what we're doing here is relatively simple. We first open 2 files, the file hello and world. And after opening, we ask NativeIO, hi, could you give me the files stored by this origin? And you get what you'd expect. We get a list or an array with 2 entries, hello and world. Now, to rename it, we first close hello. Then we again ask NativeIO to please rename hello to small. And when we listed what you'd expect, a list that says small world. Perhaps some of the things that are worth highlighting here is opening a file that doesn't exist creates it. And that's why we can just open hello and world without trying to create them first. And another important bit is that you must close hello before trying to rename it. And this is because most file system operations require the file to not have any file handles attached to it, any open file handles attached to it. This also implies that you can only open a file once at a time. You cannot open it twice at a given point in time. And that's an example of the sort of balancing act that we're trying to do with NativeIO. Like on one hand, we want to constrain the opening to only one file handle at a time because this prevents sort of the nasty bugs that come with race conditions. It also like really simplifies the spec. But on the other hand, this is a question of like, does this reduce performance? And this is some of the things we're investigating. And if it reduces performance too much, then we'll react accordingly. Here, the next example I have for you is on the file operation side of things. So it's writing and reading. And again, I'll walk you quickly through the example on the right-hand side, and then I'll highlight some of the important bits. Yeah, 2%. Here we go. Right, so we start as you'd expect. We open file foo, and we also create a write buffer that will contain the data that we're going to write. This write buffer, in reality, should be a shared array buffer, but because of the size of my screen, I've decided to only use this notation, like it's an array. And this shared array buffer contains 0, 1, 0, each of them being just a byte. Now, once we have those two things, we ask the file handle to write the buffer at offset 0, and then we also ask it, please flush yourself to disk, because we don't want to lose our important data. At this point, NativeIO has persisted this data, this 0, 1, 0, and it's already stored in a file somewhere, so it should be safe for the next session. Now, showing you here how to do the reverse, we create first a read buffer, this time of length 2, and then we ask the handle, could you please take this buffer and read starting from offset 1. The important thing to highlight here, I guess you can notice from the difference, is that the length of the buffer really affects the data that you're going to manipulate. So here we're reading only 2 bytes because the buffer is only of size 2. And you can see how the offset lets you play a little bit on the position of the buffer within the file. I think that's mostly it for what I have on the interface and sort of surface of the API side of things. I want to tell you a little bit about our Chromium implementation, because we do some funny things that are, I guess, are worth highlighting. In this diagram, it's like a very high-level overview of how NativeIO is implemented. On the leftmost side, we have the application or the website. And on the rightmost side, we have the operating system with its syscalls. So I'll walk you from left to right, especially highlighting this bifurcation that happens in the code path between the renderer and the operating system. But anyway, starting from the left over here, an application may access NativeIO either through a WASM import, directly from JavaScript, or importantly, in a lot of our use cases, they would indirectly access this to the Emscripten runtime. The Emscripten runtime is this really big JavaScript library. There's like an abstraction layer that operates between ported native code and the web and sort of translate more POSIX or CLib looking calls into something that the browser can handle. I actually have the next slide. I'll talk a little bit more about that. But anyways, it doesn't really matter which method you use. All the calls that go to NativeIO get routed to the renderer through the IDL. And here we have 2 major objects. We have the file object and we have the manager object. Here's that sort of funny bifurcation I talked about, but let me start with the bottom path. It's more classic, and then I'll highlight the difference here. So the manager object here in the bottom of the render process, it's the one that handles most of the file system operations, and it does the classical path. So if it gets a call from NativeIO, let's say opening a file, it goes through Mojo and asks the browser, could you please be a broker between me and the operating system? I'd like to open this file. Now, assuming everything goes well, the browser takes this request, talks to the operating system, and then returns to the manager. In this particular case, though, if we're opening a file, we not only return a success code or some sort of ID, but we actually return the open file handle that we got from the operating system. Using that open file handle, we then create the file object at the top of the render. And that's where we start doing our fancy trick to make NativeIO be a little bit faster. Next time that we receive an operation at the file level, let's say the application wants to read or wants to write from this file, you will first go to the render process, hit the file object, but then, because we have an open file handle, we can just go straight ahead to the operating system. And what this gives us is that we can skip this extra hop using Mojo and IPC, because directly the operation from the renderer to the operating system. And it's just an example of one of those things that we did in trying to make NativeIO sort of the lowest overhead access to storage that we can give developers. Yeah, that's sort of a high-level overview of the implementation. Of course, I'll put links to the code later in case you want to take a more detailed look. Now, I mentioned Emscripten before, and I thought, because I'm not sure how many of you have sort of played with WebAssembly or with Emscripten, I thought it was worth sort of mentioning and giving a small summary here. The slide starts with like, what is Emscripten? I would actually start a bit before and say like, what is WebAssembly? WebAssembly is a new language. It runs on a virtual machine within the browser, and this virtual machine makes very few assumptions. It's really mostly about compute and executing these instructions, right? So because it makes few assumptions, it comes with a certain set of dependencies for things that are outside executing code, and these dependencies are satisfied through imports that are part of the WASM module. Now, this is where Emscripten comes along. Emscripten is both the toolchain that you use to compile native code into a WASM module, but it also gives you the runtime, which satisfy the dependencies that come with native code. So something that look a little bit like syscalls, right? We've done quite a bit of work since we started on this project on Emscripten, because we're extending the Emscripten runtime to also contain the NativeIO file system, or the NativeIO FS. This is an extension that you can add to the Emscripten runtime, and what this does is that when you're using native code and you're just operating on file objects in C or something like that, if you're accessing files that are under a certain path, then those files are actually stored in NativeIO. So that's great. It makes it really easy for you to write everyday code outside the web and just port it and have it use all the performance benefits of NativeIO. The last thing to highlight here is on the right-hand side, I have a diagram showing the layers of how this look, because it's a bit more convoluted than that because there's a lot of communication. So if you're interested in knowing how that works, I would use this sort of as a guide and be warned that it's more complicated than the boxes and arrows. OK. That's mostly what I wanted to tell you about the API in general. I wanted to finish by talking about what we have right now, and also the open questions, or where we're looking to go forward next. So for NativeIO, it's currently in dev trial, and we've gotten relatively, actually rather good feedback, both from internal and external teams, saying like, yeah, NativeIO is fulfilling a need that we had. We also have a prototype that's currently available in Chrome behind a flag, so you can just go and try it right now if you want. And as I mentioned before a few times, we also have an Emscripten file system that you can use to make it easier to test it with native code. The last thing I mentioned is we've done quite a bit of benchmarking. We've compared NativeIO with legacy storage APIs, and we've also spent a bit of effort trying to see the difference of performance when using a synchronous versus an asynchronous surface. And this is mostly related to the way that WASM handles asynchronous code. And here are sort of the open questions. What are we looking to answer or to do in the next weeks to months? So the first thing in the list is the interaction with other storage APIs. So this is a sort of a very broad question. In the simpler case, we're thinking it probably makes sense for NativeIO files to be able to turn into the classic JavaScript file object. Right now, there's not a way to do it, but the question is, OK, what's the best way to do it? And then let's just go ahead and add it. A more complicated aspect of this side of things, though, is how does NativeIO interact with the other storage APIs that may have some similarities in the surface and may or may not, may have different constraints on the performance. In particular, we're having conversations on what's the relationship between NativeIO and the origin private file system that's part of the file system access API. Another thing that we're working on right now is on benchmarks. We're trying to come up with a benchmarking method that really testifies to NativeIO overall performance. We've done, as I said, we've measured it against legacy code, we've explored the differences in surfaces, but it would be great to come up with a benchmark that really shows like, yeah, okay, NativeIO, it really is quite fast, and it's perhaps the lowest overhead access to storage that we can do in the current state of the web. So we're working on that, trying to figure out what the best way to measure that is, and of course, make it public and reproducible. The last thing that I wanted to mention on the open questions is would love to hear about other use cases that might benefit from NativeIO. So at the beginning, I mentioned supporting these tried and true technologies like databases. I mentioned providing a file system for WASM, and I also mentioned this fine-tuning ability that we give developers. But it would be great to hear about perhaps other places where NativeIO could help. Since we're flowing along our journey to getting standardized, it would be great to hear from them, because we could act on early and make sure that we actually support these other use cases that would benefit. And thank you very much for coming. That's what I have for you. I'll leave the rest of the time for any questions you might have. But if you want to find out more of the nitty-gritty detail or leave feedback, there's a link to our explainer on GitHub. There's more detail on the decisions we've made. There's links to the code, the tutorial, and also there's an issue part where you can leave any feedback, comments, questions, suggestions. So thank you very much. Thank you. Just to start off, I did see somebody raised a hand. Oh, Alex. So I think let's just start with that. You want to?
Hey, yeah, thank you for the presentation, and this looks like great work. I'm very excited about it. So have you got early preliminary numbers, maybe I missed them at the very front, about how this performs relative to other I/O solutions for these use cases? I mean, I know that in some cases the async nature of the other ones maybe make them unsuitable, but do you have a sense for the order of magnitude in difference?
Yeah, we've done that. You're right that at the beginning we only did it using the Chrome file system, which never got standardized. And that was because, as you said, it was really hard to measure because we had this synchronous versus asynchronous issue. I can't quite remember what that result was. I think it was either 3x or 10x difference. But of course, this is sort of an older API. We are currently working on measuring against the more modern ones because we figured out a way to really test it using the asynchronous code. But
cool.
It
would also be, just from my perspective, extraordinarily helpful if there was kind of a micro benchmark that came out of this work that we could use to portably test these storage systems against each other in various browsers, because I think that would be helpful to the competition that we'd like to see.
Yeah, that's definitely something we're looking into. I see. Let me open here the list. The next person is Jeremy Roman.
Hi. So I have a couple things about your API surprised me. So I mean, firstly, it surprised me that asynchronous APIs performed so poorly, because from what I know, high performance native code has been moving toward asynchronous APIs. In fact, the Linux kernel just recently introduced a whole new one because their old asynchronous API wasn't asynchronous enough. So that was surprising to me. Was that just arising from like WebAssembly code that wasn't written to be asynchronous, and then some of the overhead in simulating synchronous behavior, or some of that is the source of that overhead, or is there something about the asynchronous execution that's slow? Because that actually was surprising me, because I would have expected you'd actually want, the WebAssembly code to just be able to throw a bunch of, things into the queue without having to call back into WebAssembly in between.
Mm-hmm. I have the meaning on this slide, right? Which the one
among other things he said, yeah.
Mm-hmm. Yes. So we've mostly taken SQLite as our sort of like ground benchmark to measure how we're doing. And SQLite was written, using more classical syscalls. We're not using any of the new fancy asynchronous storage calls. But as you said, this artifact arises from WebAssembly having a hard time dealing with asynchronous operations. So we have to use Asyncify, which adds a lot of overhead when unwinding and then rewinding the stack. So yeah, that's where that's coming from. I have to say we haven't really played much with the other, like the fancier storage options that are asynchronous at the kernel operating system level. We haven't played much with that.
Yeah. Okay. It just sort of feels like it's a little bit, backward looking, which isn't necessarily a problem when you're trying to bring stuff in for compatibility, but that like it doesn't really set the web up to be to have this as a modern capability of the web going forward. I'm also wondering if you looked at restricting use of these synchronous APIs to worker threads. We don't allow, like atomics.wait isn't allowed on the main thread because it would cause, the system to pause, and like file systems can be extremely slow. not only like you might need a physical disk to spin up, you might actually be reaching, to, an SMB or NFS drive over the network. And for the renderer main thread to pause in that situation seems like pretty undesirable.
Yeah,
like,
you're right, and I think we would not be able to standardize such a blocking instruction on the main thread. So we're definitely looking into, if we keep the synchronous version of the calls, they're only allowed in workers. There's some stuff coming up in the pipeline of WASM that may make, calling asynchronous things not a problem, and then we will be more than happy to only support the asynchronous version of the API, because that's sort of more where the web is headed, right? But if that's really not possible, we keep it on the worker, yeah.
And then finally, your use of shared array buffer surprised me. I sort of expected the general array buffer view stuff, because shared array buffers are actually distinguished by the fact that they can be mapped in other threads, and which means that now you're risking exposing to other threads the view of this IO operation in progress. And it wasn't clear to me why writing specifically into shared array buffers would be desirable. I would have expected it actually to be undesirable. Yeah,
I know what you mean. This actually comes exactly from the reason you said. So originally we added them because we wanted to, they're sort of to highlight and to make sure it works, the fact that this buffer is going to be modified in a way that's observable from the JavaScript world, right? Because you could technically observe the operating system filling it up as it goes. The shared array, NativeIO is sort of in dev trial. We're really in the process of standardization, and we know this is a problem. We would like to not stick with the shared array buffer, but they're currently there sort of as a way to signal what you're suggesting, that this buffer will be modified by a thread that's not JavaScript ready. You could observe it being modified by someone else, in this case by the operating system. But it's an active discussion we're having right now, because
but if it's a synchronous API, you actually can't observe it if it's not shared. You can only observe it if it is shared.
I'll believe you. I thought if you had a pointer to the buffer, you'd be able to observe it. To be honest, this is something that we know it's sort of an issue, and it's there as a placeholder. So I wouldn't be too worried about this sticking around till the end unless we really have to.
All right, I've taken enough time, so I'll pass to someone else.
Thank you for the questions, though. The next person is Eric Anderson.
Hi. So the current explainer kind of talks about, there is no, access across tabs. If someone's using it, they've got it. No one else can open the handle. Can you speak a little bit more about the use cases where a site would only want to work in one tab? You could say hey, I only allow this in shared workers. Or you could say, hey, this is used in a more kind of ephemeral way per tab. But can you maybe comment a little bit more on the use cases for sites that are typically loaded in more than one tab at a time?
Yeah. So the way we're looking at it for sites that require this multiple tabs operating on the same thing, we see it as you've got to go through maybe a service worker to really synchronize those things. So you only have one file in the worker, and then all the other tabs are communicating through it. That's how we envision that use case. As I said, that constraint is something we're looking into. So far, there haven't been complaints. That seems to have worked well. And we do have use cases where the use cases we've tested the most with our partners are the ones where each tab doesn't want to talk to the others, and maybe that's why we've seen it more, right? We've given the answer of service workers, and it seems to satisfy people so far. So that's how we envision it. And the last hand I got up is Dominic.
Hi. You briefly mentioned partners, and I apologize, I wasn't here for the first part of the talk, but I'd love to hear more, the focus on benchmarking and micro benchmarks from Alex's question. Are you trying to create a benchmark that really exhibits the power of NativeIO? Seems a little backwards to me. What I'd be interested in is if you take a real partner app and you implement it with current technologies and you implement it with NativeIO, how much of a difference does it make? Have you done any of those does it impact first contentful paint, time input delay, the actual user visual metrics that partners are interested in?
Yeah, definitely. So especially on an external partner that I think I won't say their name, but especially for an external partner, they've been working on a project for a while, and they were using whatever is right now on the platform. And they kept coming back to us saying, like, well, like, this works, but it's really slow and painful, and they haven't managed a way to sort of like hack it around to make it fast. And that was actually really, really encouraging when we worked with them, because when we gave them the first draft of NativeIO, they were like, oh yeah, perfect. This is really like covering that need, and it's really like they said they can see the difference in the performance. So that being said, this has been, I don't think we have numbers. We only have sort of like the testimonies from the engineers working on that project, but we've heard.
Okay, yeah, I would. That's really great to hear. I would love to, or I would encourage you to lean into that kind of scenario and try and get numbers from them, ideally publicly reproducible numbers, but I know that's hard with partners. Because I think that's what would really sell this API more than micro benchmarks, at least to me.
Okay, I mean, I think like that's good advice. Thank you. We're probably going to end up with a mix, of course, but we'll focus on that. Thanks. I think Francis, you're up.
Yeah, so actually my question is slightly the opposite of Dominic. So you say that when you're reading and writing, it's 30 times slower when you're using Asyncify. Can you speak a little bit about that? What's the granularity of the I/O operation? Is it 1K buffer or what? How often do you sort of? How often do you switch?
Right. That is fully controlled by the application. It depends on the buffer size, and we were using a benchmark that comes with SQLite, the one they use to measure changes in their sort of in the time it takes whenever they make a change. I seem to remember 4096 bytes as a very common number floated around, but I'm sure that benchmark really moved the size of the buffers a lot depending on which test this was doing. So this particular result, this 30x, was using whatever the speed test was using for SQLite, which they claim represents, if you can make that claim, a normal workload on top of an SQLite database. Thankfully, and Richard is on this call, he's working a lot on a benchmark that it will be much more easier to understand and it's reproducible. So on the report on that one, we'll definitely make sure to highlight those sort of as more details, like what's the most common buffer size being used and stuff like that.
Yeah, I mean, these numbers are significantly worse than I would have expected for using Asyncify.
I agree. Like, we were surprised by them, especially because we saw Alon's work when benchmarking Asyncify, and it was not this bad. I mean, the good news is that it's only 3x in the overall execution of the program. But it was very surprising, which is why I add that little caveat at the end, right? Like, this was our preliminary results. It takes quite a bit to set up this benchmark, which is why we haven't published it properly, like so people can run it themselves. So this needs to be verified. But from the work of a few months, we were also surprised, and we're trying to figure out, okay, why is that so slow using this sort of like standard benchmark?
Great, thanks.
Problem. All right. I think there's no more raised hands, and we're also, I think, out of time, if I'm right. So thank you very much for coming. If you have any questions or comments, please reach out to me through the explainer. My email is also all the way over here, and the @Chromium. Thank you very much for coming.